Good everyone, I welcome you back to another episode of Mathematics for SS2 or Senior Secondary School 2. And in this episode, we'll be doing a continuation of what we stepped off from in Mathematics for Senior Secondary School 1 and Mathematics for SS1. We'll talk about logical reasoning. We'll talk about the first part of logical reasoning. Now, in this Mathematics for SS2, we are going to be stepping up from there, climbing higher a bit, and then we're going to be talking about the second part of logical reasoning. And in this episode, we'll be talking about a revision of what we covered in the first part. Then in this episode, we'll also be talking about a valid argument. What is the condition for an argument to be valid? So when we talk about that, we'll also talk about the truth statement, how you represent them with the use of Venn diagrams. So let's continue. In this episode, let's start from the 5 connectives. Now, in the previous episode, if you've not checked about the logical reasoning in part 1, go and check that out. And in this episode, we'll be talking about how you represent each of those connectives I talked about in the first episode. We're talking about how to represent them using the Venn diagram. So we know we have 5 connectives, right? The 5 connectives are the negation connective, the disjunctive connective or the disjunction connective, the conjunction connective, the implication connective, and the equivalence connective. So now each of these ones has their truth values or has their truth tables, and you can also check them out in the first video. So let's continue from there. Let's talk about negation. So how do you represent negation with Venn diagrams? So if this is your universal set, universal set, and then this is a set A, then if this is set A, then the negation of set A is basically the area of that universal set that does not contain set A. So if this circle set represents a simple proposition, then the negation is basically the area outside that circle. So that means this area here outside the circle. That will be the negation. So I just hatched the area outside the circle. So this will be the negation of the proposition. So that is how we represent negation. Then next, let's talk about conjunction. Now, in the conjunctive statement is the and connective. So this conjunction involves two simple statements. So if these simple statements are the set A and B, then the conjunction of these two statements is the intersection of them. So that is this little area that represents where they meet. That will be the conjunction. That will be the area. That is the intersection of this. It's also represented as A intersection B. While the negation of a statement is represented by not A, or you can also call it A complement. So that is how you represent some of these. And in this same area, the disjunction of the statement will be the area that does not contain any of these two sets. That will be the area outside. So if you shade this area outside, this large area outside these first two sets. So this area outside the first two sets that I just shaded now is the disjunction. The area outside like this is the disjunction. Then the area between them is the conjunction. So and then we also have implication. That is when the sets are equal. So that is an implication. Then when we have when we have equivalence. Equivalence means when the sets are equal. Then implication means for one to happen, another has to happen. So that means if A, then B. So we will not represent that on the Venn diagram implication. So but we've represented not statement, the conjunction statement, the disjunction statement outside, then the equivalence statement when the sets are equal. For example, if set A, if A is equals to B, or equivalent, so rather let's make it equivalent. If A is equivalent, that's logical reasoning for this biconditional statement. An equivalent statement is also known as a biconditional statement, and it's called a biconditional statement because the arrows go in both directions. So this arrow can go forward and also go backward. It's a biconditional statement. And if you are a chemistry student, you will also use it to remember that this is also a representation of a double reaction, or rather an equilibrium reaction. So an equilibrium reaction is basically dynamic equilibrium when the forward reaction and the backward reaction can take place. So that was, I just diverged into chemistry. Let's go back to mathematics. So now let's go to the major work for this video. We'll talk about the truth values of the truth tables, and if you still don't know them, you can check that in the first episode. Talk about the validity of a statement. So what are the conditions to meet before a statement will be valid? So let me give an example. Determine the validity of the argument below with premise x1 and x2 and conclusion s. So x1, the first premise or the first simple statement states all doctors are intelligent. That's the first premise. So rather this is a premise, and a premise is rather a condition of is rather a combination of one or more or two or more, rather let's say one or more simple statements. That is a premise. Then we have the conclusion. A conclusion is formed when you combine your premises together. So the first premise x1 states all doctors are intelligent. That's the first premise. Then the second premise is some Nigerian doctors are intelligent. Then some Nigerians are doctors. That's the second premise. Then the last premise, or rather the conclusion, is some Nigerians are intelligent. So the first premise x1, all doctors are intelligent. The second premise, some Nigerians are doctors. The third premise, some Nigerians are intelligent. So you have to represent that in a Venn diagram. So let's use the Venn diagram to test the validity. So let this be the universal set, the set of all people. This is the universal set, all human beings. Now let this first set I, represent the intelligent people. So this set I represents the intelligent people, I. Then this set D of doctors represents the people that are doctors, because the first statement says all doctors are intelligent. So that means the set of doctors is a subset of the set of intelligent people. So that's all doctors are intelligent. So all the doctors will be inside the intelligent set. That's how you represent it. So that shows that all the doctors are intelligent, because once something is an element of set A of doctors, let's call it set D of doctors. Once it's an element of set D of doctors, then it has to be an element of intelligence. You can see doctor set is inside intelligence set. Then lastly, we have the second statement says some Nigerians are doctors. So if we have a set of Nigerians, that means if we have the set of Nigerians, then part of that set will enter into the set of doctors. So that means let's represent as this. So there will be an intersection between the set of Nigerians and the set of doctors. That means not all Nigerians are doctors, but some are doctors. So you can say that there's an intersection. Now let's verify. So is it true that some Nigerians are intelligent? So if some Nigerians are doctors, is it true that some Nigerians are intelligent? So let's check. We want to see if there's an intersection between this set of I and the set of D. So you can see that there's an intersection. You can see this area is intersection between the sets I and D. So that satisfies the condition that once a Nigerian is intelligent, there's a possibility that he is also once there's a Nigerian, there's a possibility that it's also intelligent, because there's an intersection between the set of Nigeria and the set of intelligence. So this intersection shows that this argument is valid. So that means it's valid that some Nigerians are intelligent. That is valid. So and then this is one of the methods of verifying a compound proposition, to verify the validity. You can see that this argument consists of three compound statements. So the first one was all doctors are intelligent, some Nigerians are doctors, and lastly the conclusion, some Nigerians are intelligent. So when you have a combination like this, it's an argument, and an argument can either be true or false. So we have true argument, and a true argument, when all the truth values are true for an argument, it's called a tautology. So that is an example, but that is beyond our mathematics course for this video. So moving on to the next stage, let's talk about the chain rule. Now the chain rule is basically an implication which says that if we have x implies y, then we have y implies z, then we can safely say that x implies z. So this chain rule, this implication is also known as a chain rule. When you have three implication statements and then you combine them together, x implies y, y implies z, then x implies z. That is the chain rule, and it's often true. So let's give an example. So we have, in the following argument, determine whether or not the conclusion necessarily follows from the given premises. So once it forms a chain rule, you can basically be satisfied that the conclusion follows from the premises. So the first statement is all dog drivers are careful. So let the set D be, let the statement D be x is a driver, x is driver. So when a person is a driver, it will be x is a driver. That will be set D. Then the next set will be when a person is careful, let's say x is careful. That will be set C, or rather statement C. Then lastly we have let the last set will be people who are patient, x is patient. Let this be statement P. So the statement D stands for X is a driver, the statement X stands for X is careful, the statement P stands for X is patient. Now we have to test that the first premise say that all drivers are careful. So we can represent this in mathematics that if X is a driver, then X is careful. So if X is a driver, statement D implies statement C. So D implies C. D implies C. The next we have people who, careful people are patient. That's the second premise. So careful people are patient. That means if X is careful, then X is patient. So C implies P. Then lastly, we have the last one, which is the conclusion, is that therefore all drivers are patient. So that means all drivers, this set drivers will be set of patient. D implies P. D implies P. So the question here is to describe is to answer whether is this valid. So does this follow chain rule? No, chain rule states that X implies Y, Y implies Z, X implies Z. So if D implies C and C implies P, does that mean that D implies P? That is true, because that corresponds to chain rule, which says that if the first implies the second and the second implies the third, that means the first will imply the third. So D is the first, C is the second, and P is the third. So if D implies the third, that's first implies the third. It also follows chain rule. That is true. So to recap, we've talked about the representation of the connective using Venn diagrams, and then lastly we applied Venn diagrams to solving one statement to test the validity of an argument. Then lastly we now apply chain rule to test the validity of another argument. So this episode is all about testing the validity of logical arguments and using two methods, using the first method of Venn diagrams and then using the second method of chain rule, which says that if X implies Y and Y implies Z, then X implies Z. So I hope you have enjoyed this video. Don't forget to like, share and subscribe in order for me to be able to post encouraging and educational content like this. Thank you for watching.